In this video, I'm going to focus on Module 6 Multiple Choice Questions, 2005 HSC exam. The first question, in a particular experiment, a long length of copper wire of very low resistance. So we have copper wire, very low resistance, is rotated by two students. The end of wire are connected to a galvanometer and a current is detected. Which of the following is least likely to affect the amount of current produced? Okay. Firstly, we need to see why we have induced current in this wire. The wire is in the Earth's magnetic field. As it's rotated by two students, it experiences a change in magnetic flux. And as Faraday's law, a current is induced in the wire. To find out what factors the magnitude of current depends on, let's look at a formula. Okay. We know the formula like for Faraday's law. That epsilon is equal minus n delta phi delta t. And we know phi, that is magnetic flux, is equal B times A. That B is magnetic field and A is the area. In our case, because we have one wire, so N equal 1. So I can write it simply minus delta phi, and because phi is equal BA, I can write it like delta BA delta T. And as we know, the magnitude of magnetic field of Earth is constant, I can write it this way, minus B delta A to delta T. And we know A equal, so I write A equal L times delta X divided by delta T. That L is length of wire and delta X is the width of area that by rotating wire it covers. And if I say delta X to delta T, as we know, is equal speed, or we can say velocity, but in this case it doesn't matter, I say speed. So as a result, I get a formula minus B, and because it's constant, I can put it out here, writing minus B, L, and delta X to delta T, so it shouldn't be here, phi. So we see epsilon actually depends on magnitude of magnetic field, length of wire, and speed of rotation. Let's see here. Which of the following is least likely to affect the amount of current produced? The length of rotating wire, as we can see in the formula, definitely it affects that. The speed, yes, it affects that. Where the wire is orientated north, south, or east, west, yes, it affects the magnitude of epsilon. Why? Because we know the direction should be perpendicular to the direction of magnetic field. So the direction of rotation should be perpendicular to the direction of magnetic field of Earth. So it's important which direction is orientated. But what about the thickness of the rotating wire? We see there is no factor here to show the thickness of wire is important. So the answer is B. Let's go to next question. A single turn coil of wire is placed in a uniform magnetic field. So we have a uniform magnetic field and we have this coil inside that and at right angle to the plane of the coil as shown in the diagram. The coil is then rotated in a clockwise direction. Which of the following shows the direction of current flow in the coil as it begins to rotate? So definitely we know we need to use right hand rule. Okay, how we can use it? if the magnetic field, if we consider the magnetic field is on the page, the force on right side wire, the force on right side wire, I mean this wire, is into the page. So by considering the right hand rule, so the direction of current is what is shown in B. So, no, sorry, in A. So the answer is A. Let's go to next question. The primary coil of a transformer is connected to a battery, a resistor, and a switch. The secondary coil is connected to a galvanometer. Which of the following graphs best shows the current flow in the galvanometer when the switch is closed? Okay, as we can see, let's see. Here we see this is our primary coil. So I write primary coil. And this one is secondary coil. What else we can see here? We see it's connected to a source of DC voltage. And here is we have switch. Okay. A change in magnetic flux of the primary coil induces a current in the secondary coil as Faraday's law. In this example, the primary coil is connected to a DC voltage. So there is no continuous change in the magnetic flux. So by closing the switch, a change in the magnetic flux happens. When we close the switch, something that happens. For that moment, there is a change in magnetic flux, and as a result, a current is induced in the secondary coil. However, it drops to zero again. Why? Because when you close the switch, after that, again, you don't have any change in magnetic flux. So as a result, the induced current should drop to zero. Right now, let's look at the answer. Which answer can be right? Definitely this one can't be right because there is no induced current. This one can't be right because we can't see the current drops to zero. It's a constant amount, but we don't have any constant change in magnetic flux, so definitely can't be correct. This one can't be correct because we have induced current, it drops to zero, and again we have induced current in the opposite direction. This one can be correct if we close the switch and then again we open it. So we have a change in magnetic flux when we close the switch, and then for the second time when you open the switch, again you have a change in magnetic flux, but definitely the direction of current is opposite. So this one is correct if you close and open the switch, but this one, when you just close the switch and you don't open it again, so you see you have a current, induced current, and it drops to zero again. So the answer is C. Let's go to next question. Question 9 of 2005. 3 rings are dropped at the same time over identical magnets as shown. Which of the following describes the order in which the rings P, Q, and R reach the bottom of the magnet? Okay, let's look at here, see what we have. Here we have a plastic that we drop in this tube that is magnet. Definitely between plastic and a magnet, there is no interaction, so it falls as a result of gravity. So no interaction here. Or I can say no eddy current here, or no eddy current, because it's plastic, and for eddy current, we know we need a metal. And let's look at R. Again, I see the copper. I know copper is a metal, so we expect to have eddy current here that oppose the change in magnetic flux. So because we drop this one, we expect an eddy current here that opposes the change, that should slow this one down. But here you can see this cut. So as a result that you see the cut, you know electricity has to flow in a complete circuit. Or I can say here, complete circle, but I don't have a circle. Do I have it here? No. So as a result, I don't have no eddy current at cut. So as a result, no eddy current. Okay. So no eddy current here, no eddy current here. So both of them drop as a result of gravity. What about this one? It's a copper, a metal, and definitely it has eddy current. And we know the direction of eddy current should be somehow to oppose the change. So if you drop it, the direction of eddy current needs to oppose the change, so make a force upward, so it slows down the copper. So as a result, the answer should be rings P and Q arrive simultaneously, followed by Q, that is this one, that is the slowest. So the answer should be C. Let's go to question 10. A transformer is to be designed so that it's efficient with heating by eddy current minimized. Okay. The designer has some iron and insulating material available to build the transformer core. Okay. The windings are to be made with insulated copper wire. Which of the following design minimizes the energy losses in the core? Okay, a solid core loses energy as heat because it makes eddy current, so it loses a lot of energy. To overcome this problem, the core actually made of very thin lamination, as you can see here, and you can see some here. But to minimize the size of surface perpendicular to the magnetic field, if we minimize the size of surface perpendicular to the magnetic field, we can minimize the amount of eddy current. So if you look at all answers, this one definitely is nothing, but about the rest of that, we can see only part B. The core is laminated somehow, that is minimize the size of surface perpendicular to the magnetic field, and as a result, it minimizes the amount of eddy current. Minimizing the amount of eddy current minimizes the loss of energy as heat.